That's annoying. It's a little off center.
Okay. All right, that's fine. Oh. Couple of more things. Bless you. Let's see. Let's do attendance while we're getting started. Okay, Abigail. Hey, Abigail. Welcome. I saw Jasmine somewhere in the front. Yeah. Teresa is here. Yep. Saw you come in. I saw Chris come in. Saw Knox come in. Cameron. Cameron's not here yet. Annie. Do I see Annie in the corner? Shane is not here yet. Oh, there's Shane right there, actually. Marley's not here yet. Kayla, I saw Kayla come in. Hi. Marcus, I saw Marcus. Met Diana. April, I saw April come in. Hi. Angel's here. Dan's here. Alex is here. Corinne, can I see you? I saw it. Yeah. Oh, Alyssa, right there in the corner. Emily, not here yet. Zach's here. Lucy's sick. She may or may not be on the Zoom. But not yet. Rebecca? Hi, Rebecca. Welcome. And Ryan. Ryan here, yeah, in the corner. Awesome. Okay. Got a couple more minutes. Oh, well, it's time. Welcome. Oh, there we go. Sorry. No, that's okay. I just about to get started. Thank you, guys. It's still fun. Yep. I haven't even finished my first sentence yet. All right, welcome to quantum mechanics. Formerly known as physical chemistry 2, but quantum mechanics. That sounds really scary. I'm hoping to convince you this semester that it is in fact not scary to take quantum mechanics. And quantum mechanics really isn't that bad. It's got a bad rep. And today I kind of want to explain why. And the problem is not with quantum mechanics why it's difficult. I'm sure you've heard of, whether you know what quantum mechanics is or not, we'll talk about that. If you've heard of it, you probably know it's got a bit of a reputation. And that reputation really doesn't have to do with the difficulty of the material. We will be dealing with things that are somewhat complicated mathematically, but really not any more complicated than we did the last semester. Do some integrals. We actually may look at some matrices and vectors, some matrix math and vector math, depending on how we feel. The problem, the hard part of quantum mechanics is your mind. It requires you have to understand that as a person. In some ways, all humans are scientists in that we take empirical evidence, we do things, and we learn from mistakes, or we do something and we see a response, and we come up with some logical system of understanding about how things work, right? We just do it on our own, right? You swing a bat and hit a baseball, and baseball goes flying. The harder you hit the baseball, the further it goes. Right? And you can do all of this stuff. Quantum mechanics, you don't have that luxury. Everything in quantum mechanics, for the most part, or rather the really key parts of quantum mechanics to really understand how atoms and molecules work microscopically, or anything works microscopically. Because we'll see that some of these effects happen in things much larger than molecules. Is actually very straightforward in terms of theory, but it does not compute when you think about what you understand empirically about how the world works. All right, and I have a thought experiment, kind of a fun little lecture to do today. No math required, just a little bit of logic to make up a fun experiment to do with electrons. Do it on the board. And what you're going to find is that the result from these experiments are completely contrary to what you expect. Right? And the first couple of weeks of this course, maybe the first 3 lectures or so. So I'm going to illustrate things, what I would call experimental facts of life, things that we observe about molecules and atoms, and small microscopic things in general, that are completely contrary to what you understand from classical physics, right? Newton's equation, thermodynamics, right? Things that you've studied already, right? They're very logical things, right? Newton's laws, right? We're going to find that these things break down microscopically. And the world is, at the microscopic level, the world looks very, very different. And that's why quantum mechanics is very difficult, not because of the actual difficulty of the material, but because it appeals to a kind of logic and thinking strategy about how the world works that is completely contrary to what you've experienced for the past 20 or 22 years. Right? And that's not your fault. No one's fault. The fact of the matter is, it's just that the microscopic world looks very different than the macroscopic world. And you have to free your mind. You have to take the quantum red pill, if you will, in order to really appreciate that. And that takes time. It took me years. And so you're going to come out of this class probably more confused than you came in. Maybe you understand some things. But this is material that the introduction is just so mind-blowing, and you have to reconfigure the way you think. Spend so much time doing that when you come to the end, you're like, well, I barely learned anything because I've just been redoing myself mentally. But then when you go back and return to the material, you start thinking about it more. Like, for instance, the second time I took the course as a student, which I did in graduate school, everything started to make sense, started to come together. Because I'm starting to reprogram my mind, starting to think like a microscopic particle. And once you get yourself into understanding and being comfortable with that, the math works out much more simple. All right, and in some ways, as I'll show you, the math for quantum mechanics, the physics, the set of equations that we use, right? And Nico Pawlowski's class, right, when you do physics 1, for instance, you learn Newton's laws. If you go further, you learn Hamilton's equations, Lagrange's equations for motion. Those are very complicated differential equations. They're nonlinear. I'll explain what that means in about a week or so, what I mean by nonlinear. They're very, very hard. And one of the examples, a really great example of why classical physics is actually really hard, is to think about orbits. Maybe you guys remember this from intro physics. You probably learned the two-body interaction system, right? We have two spheres and they're orbiting each other. You can set it to the center of mass, and you can look at what they call the barycenter, right? You can look at the motion of one particle with respect to the other. The two-body system is exactly solvable. You can calculate the trajectories of those particles. Right? If you have, say, like just the moon and the earth in the vacuum, right? Very easy to do that math. The moment you add a third body, you can't solve the equations anymore. Right? Three-body problem is unsolvable. Right? If you've ever read those Chinese sci-fi novels, The Three-Body Problem, they talk about this a lot. Right? And that's because physics, we'll talk a little more about this later, classical physics, right? Newton's laws are nonlinear, which means that the physics of one object is not this, and if you take the physics of one object and you have three of them, the physics of three objects is not the sum of three individual objects. The physics of three objects is very different than the sum. The sum is greater than, the total is greater than the sum of parts, right? The interactions of three bodies is more complicated than just three independent bodies. In quantum mechanics, that's not a problem. Quantum mechanics is linear. So if you understand the physics of one particle, you understand the physics of n particles, right? And that's how we're going to build up chemistry. We're going to understand how a single electron orbits a nucleus. And then we're going to say, well, what about, which is hydrogen, of course. The question is, what are we going to helium? We now have two electrons and a nuclei, three bodies. Well, how are we going to solve that problem? Well, we're going to treat the helium atom like two hydrogen atoms added together in the same space, right? We're going to treat a two electron problem as two one electron problems. And we're going to find that that works. It doesn't work perfectly, but it gives us a framework in which to actually calculate the correct result for helium and understand how helium works. You can't do that in intro physics, in Newtonian physics. The moment you have three bodies, everything falls apart, right? The math is incredibly complicated. You're not even guaranteed to have a stable orbit between three bodies. But in quantum mechanics, we can show that you can. And we can analyze that physics and how an atom works by thinking about how one electron orbits a proton and then add another. And so we're going to be able to build up, kind of bootstrap chemistry from the ground up. We understand how electron works. We understand how the hydrogen atom works. We can understand how all atoms work. And once we have atoms, we can put them together to make molecules. We can make the simplest molecule in the world, H2, two hydrogen atoms together, two electrons, and then use that theory to build more complicated bonds, more complicated bonds. Right? We're going to bootstrap up. And quantum mechanics allows us to do this, right? You can't do this in intro physics in the same, or in Newtonian physics. So it's in some ways, it's very simple. In Newtonian physics, you can't do that. But in quantum mechanics, you can, right? You can understand a small problem and then just multiply, and then a bigger problem is just a sum of smaller things, right? So we're going to have to get around that, and that's the easy part. The hard part is that some of the things that we predict are going to be very counterintuitive, and we're going to have to understand the logic of why these things are counterintuitive, and that you're going to have to understand is that quantum mechanics is not hard or wrong. That you've been lied to for all these years, and actually what it is that physical reality at the microscopic level, right? When macroscopic level, right? Things on the scale of us is an incomplete understanding of how the universe works, right? It's an approximation, right? And so we're going to go one deeper, and we're going to realize that it's an approximation for a more complex sort of elegant theory called quantum mechanics. And really what happens at the microscopic level also happens at the macroscopic level. We just don't see it. These things are too small for us to see. So when you get to small enough length scales, small enough microscopic particles, we start to see those physics dominate. They're always there. They always have been. We're just not able to see them because we as macroscopic objects are not privy to understand what happens in the microscopic world, right? Until quantum mechanics. All right, so before we really dig into it, I kind of want to, it's really important to talk about history a little bit, talk about kind of the background, the motivation for quantum mechanics. It's such an important story and has a lot of really great characters. And so what I want to do for the next two lectures is talk about some of these experimental facts of life, things that we observe in experiment that Newton can't explain for us, or Maxwell, for instance, for the electromagnetism. Right? And so before I do that, let's just talk very briefly about the syllabus. There's a couple of new people in here. So I'm going to skim through most of this. If you don't know me, I'm Professor Seifert. I have already picked out my office hours. They're right here on the board, Friday and Tuesday. I have kind of a tight schedule, so that's kind of where I'm at. I might have availability on Thursdays as well. If you need to find me on another date, just let me know, and we'll figure it out. I am available Monday and Wednesday mornings, but I'm just schedule with me. If you want to meet Monday or Wednesday, just let me know, and I'll schedule that. Sean's your LA. I don't know where Sean is. He should be here, but he's not. We only have one LA this semester. Sean will be for both sections. So you'll see him about half the time. Right? He's going to split his time between both sections. I'll let him schedule some times for you guys. It's the same thing as before. Homework, things like that, same as last semester, 5 problem sets, 2 take-homes. Exact same grading. For those who are new, I sent you an email. If you're still confused about things, just pull me aside about that. Let's talk a little bit about what we're going to talk about today, or this semester. Again, I've split it up into 5 modules. We're going to spend quite a bit of time, maybe the first month or so, talking about quantum mechanics, building up our toolkit, right? And kind of like, just like we do in thermodynamics, we have the 3 laws, or in physics, you have Newton's laws. We have these laws, or we call them postulates. These are things that we assume to be true. And we're going to talk about this. We're going to talk about what it means to be a quantum mechanical system. And then we're going to start applying it. That's all we're going to do. We're just going to apply. We're going to have one set of rules. And it'll take one or two lectures to kind of list those rules and go through them. We're going to have a couple lectures because we got to deal with, there's going to be some new math that we got to do, some new techniques. And then we're just going to apply it. The first thing we're going to apply to are, well, 3 examples. The first example is my favorite, what's called the particle in the box. We're going to take an electron and trap it in a box with infinitely high walls, and we're going to see what happens, right? That's kind of a classic example. And we'll be able to see this quantum mechanical behavior very simply in these boxes. And then we're going to start thinking about systems that are more chemical, right? And what I want to tell you in some ways is that all molecules are in some way are giant boxes that vibrate and rotate, right? They've got bonds that can vibrate. The whole molecules can rotate. They can rotate end on end. And so we're going to think about the quantum mechanics of vibrating things and rotating things. And so the models we're going to use are springs and tops. Right? We're going to treat our molecules like spinning tops and vibrating springs. So we'll talk about the physics of these things, talk about how these are associated with chemistry. Obviously, bonds we're going to treat like springs. They have some stiffness, they vibrate. So this will teach us a model for the bond, and spinning top will teach us about rotation, which is very important, but not always appreciated in chemistry. I have to talk about it because that's my research specialty, rotational spectroscopy. So I like to spin moments. Once we have that information, it turns out that's more or less enough to start tackling the hydrogen. Right? So once we understand how things vibrate and how they spin, we can use that physics and apply it to the situation of taking a proton and an electron and putting them in an orbit, if you will, binding them together. Right? So we'll spend about 2 weeks on the hydrogen atom, building the hydrogen atom. We will be able to write down a set of equations that will tell us everything we need to know about the hydrogen atom. We will be able to write an equation for the hydrogen atom on the board. It will have a result, an answer, or a set of answers that allow us to calculate anything precisely about the hydrogen. Right? We'll actually be able to do chemistry from the ground up. We'll also talk about, as we add more electrons, of course, right? Hydrogen is always so interesting. We'll talk about having multiple electrons in an atom. And then what we're going to do is we're going to add atoms together to make molecules. Right? So we'll talk about something called molecular orbital theory. It's the basic basic theory of how you construct molecules from atoms. And then finally, we're going to close it off with my favorite topic, which is spectroscopy. And spectroscopy is what I would call applied quantum mechanics. There is no spectroscopy without quantum mechanics. Spectroscopy is quantum mechanics. It is how we do quantum mechanics in the lab, right? We use light. Light will end up being an extremely useful tool for us to probe chemistry. And spectroscopy is the key to that. Right? So we'll talk about the fundamentals of spectroscopy. And we're going to break that mold, that ideal that you have in general chemistry of spectroscopy being an atom absorbing a photon of energy packet of light, an electron or something being excited formally to an excited state, and then at some point emitting later. Right? We're going to break that. That's not accurate. Right? That's a very, very crude approximation of what really happens when a molecule absorbs a photon. And so I want to teach you guys the right way of how to think about a molecule or an atom absorbing or emitting a light in a spectroscopic experiment. Okay? The actual physics, the actual dynamics of this is very, very interesting, and it's very beautiful. And it will draw from Einstein and a whole number of other very famous physicists who dealt with this problem, including, and one of the most important is actually Oppenheimer. So that movie, they didn't actually talk about Oppenheimer's impact and contribution to spectroscopy, but in some ways, the reason why we do molecular spectroscopy, why it's a viable technique is proven. That was demonstrated to be something that you can do by J. Robert Oppenheimer. It was his PhD work with Max Born in Germany. Right? So Oppenheimer is very, very important in this story, as well as Einstein. So that will be our goals this semester. The way that the homework will work, each module will have a problem set, 2.5 week problem set, you know the drill. And then we'll have a take home, hopefully due right before spring break, maybe after spring break, I don't know, we'll just see how it goes. So that will cover everything up through the atom. And then we'll have a final, which will just be on molecules and spectroscopy. So we'll have kind of just everything up to the hydrogen atom and then molecules and basically polyatomic molecules for the final. Any questions? Okay. All right, that's all I got to say about that. Some other things that have changed since last semester. Let me share my screen. I have decided to partially, we'll see how well it works, to a digital whiteboard. So I've got this rather expensive writing tablet here. And I'll be able to do my board work, hopefully mostly on here. This will allow me to save all my board work on PDF and then post it over. Okay, so if you guys get caught behind, or I know a lot of you put your phones on and take pictures of the boards, you won't have to do that, right? Because I'll just write it on here. If we feel like this doesn't work very well, then I'll ditch it. In this room especially, I'd really like to work on the boards because there's so many. But in the other section, I have like 2 really shitty boards that are like half this width. So I can't do board work in that class. So I had to come to something. So we'll be working on this. One more thing I wanted to say before we get started. Just some of you have already submitted it. As usual, there's an introductory survey assignment on Canvas. Just complete that before, I don't know when I have it due, January 22nd before class. So next Monday. It's really easy, 30 seconds. And if you turn it in, you get a free late submission, just like last semester. So let me make sure you do that. There's some questions about what kind of topics we're going to do this semester. I'll let you guys choose what kind of focus you want in this class. For a couple of things. Any other questions? Okay. I want to start today, if it lets me. Oh, I know the problem. With a thought experiment. And a really, really easy one. And it's going to demonstrate something very, very critical about quantum mechanics. That's going, I don't know if it's going to blow your mind, but it's certainly going to confuse you. And it confused me at first. But I'm hoping that by the end of the semester, and actually we're getting even closer to that, we'll understand why this is. But it's really important. What I want to do is this. I want you to consider an experiment. What I'm going to do is I'm going to have some experiment here. And this is really sloppy, but I have a gun. Yeah, I know. That shoots out electrons. Right? Now, there is actually something called an electron gun. If you've ever owned a CRT TV, a cathode ray tube, the back of the cathode ray, all a cathode ray tube is a phosphorescent screen and a giant gun in the back that shoots electrons. There's the electron. All right. And electrons aren't that interesting. I'll talk about this. In fact, I think on Tuesday I'll have a brief lecture on subatomic particles. We should understand what atoms are made out of before we do anything. Just to remind you, I'm sure you guys are familiar with electrons, but I'll make sure everyone's on the same page next week. Electrons aren't that interesting. Electrons have no shape; they're point-like particles. Right. So let's write down some ideas or some things about this. So first of all, the most important thing about an electron, it has a charge. What's the charge of an electron? Charge of an electron is negative what? 1. It's easy enough. Please dedicate that to memory if you don't know it. Well, again, I'll talk about these next week. Right? Electron has a -1 charge. Right? Every electron contributes 1 unit of negative charge. The size of an electron, well, it has no size as far as we can tell. It's a point. Right? So I can't tell you what the diameter of an electron is because it doesn't have a diameter. People look for it, look for a measurement of it. There's a prediction that if it does have the size, the electron should have a dipole, but it should have a positive pole and a negative pole. But no one's ever been able to see that. So as far as we know, it's a point charge. And of course, it's very, very small. Right? So the mass is on the order of 10 to the -30 kilograms. All right, so they're really, really small particles. But they are particles. All right? I can prove to you that they're particles, or that we can represent them as little bullets because of your CRT TV. Right, a cathode ray tube television, you have an electron gun, and depending on where you want your image to display, it shoots an electron at that part of the screen. Right, the only way you can do that is if it were a particle. Right, you're going to shoot a particle at a specific point on your screen, and so yeah, electrons are particles. All right, what I'm going to do today now, electrons have one other characteristic, but I'm not going to tell you what it is yet, because if I tell you what it is, we're going to get confused by it. And the other property it has is called spin. I'm not going to talk about spin. All right. So instead, what I'm going to do is, and bear with me, is make up some fake properties for my electron instead of using the word spin. Okay. I don't want to think about spin right now. I just want to think about electron having properties. And what we're going to find is that spin is kind of a black and white for an electron. It can either be one value or another. There's only 2 options. Electrons come in 2 flavors, if you will. So let's say electrons have flavors. Right? So we'll say they're either sweet or savory. Now, we call that spin. But let's say they have another property as well. What's another? Someone give me something clever. What's a property that we can like choose 2 different things? We can do color, black and white if you want, but maybe something more clever. Any ideas? Okay, I didn't think so. All right, we'll do color. So let's say that electrons can either be black or white. Okay, flavor and color are not related to each other, obviously. Right? I'll make that claim, but you should probably understand that it being sleek or slavery has nothing to do whether it's black or white. They're two entirely orthogonal concepts. Okay. And what I'm going to do is I'm going to build an experiment where I build two boxes, two apparatuses. Right. So we're going to first one we're going to do is a color box, a color. Let's call it a color measurement, color spectrometer, color. We'll just call it a color box. All right, and the color box is going to work really easy, really simple. It's going to be a box. Does not matter how it works. But an electron goes in, and if the electron is white, it comes out here. And if it's black, it comes out here. Simple as that, right? We have some magical way it takes an electron and it reads out black or white. All right, and we're going to do the same thing for flavor. We have a magical box that takes an electron in and spits out the electron this way, if it's white. And just because I don't have space, I'm going to draw it this way, black. Pretty straightforward. Now, it turns out that if we just say this, because this might seem absurd. If I replace flavor and color with spin, you can do this experiment. I mean, you can't personally, but people can do this experiment. All of this is real. I'm just changing the names of the properties. So I don't want to worry about that right now. All right, so here's my two boxes. So this is what I'm going to do. Very, very simple experiment. Yeah, go ahead. Oh, sorry. Thank you. Sorry. Yeah, I apologize. You are correct. We'll do sweet. We'll do sweet going out the same way it came, and then savory on this side. Okay. All right, so let's do a very, very simple experiment. So the first thing I want to tell you, I just want you to keep this in your mind, that every electron is identical. You can't distinguish between one electron or another, right? Well, we'll talk more about this as the class continues. And this is a really important part of microscopic particles. This is true for atoms, true for protons, true for any particle you microscopic particle you think of. Every atom is identical to each other, or every electron is identical. They're indistinguishable. I cannot, it's impossible for me. If I had a box of 10 electrons, I can't mark them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can't do that. You can only count the number that you have. You can't distinguish between them. They're indistinguishable particles, right? Turns out to be a super essential concept later on. Don't have to worry about it. Just accept that I can't tell the difference between two electrons, right? I just know they're electrons. They're all the same. All right, so I'm going to do a really, really simple experiment. I'm going to call this box the F box and this the C box, so I don't have to keep typing it. All right, so what I'm going to do, my first experiment is I'm going to put in a random electron, and I'm going to put it through the color box. And I am going to measure on either end with my measurement device. The measurement device will be these little boxes like this. Right, these are my little sensors. We can call them little CCDs, little CCD cameras. Right, and they're little things that'll light up when an electron hits them. Okay, little detectors. All right, so I'm going to run 100 electrons, 1,000, a bunch of electrons are all identical through this box one at a time. All right, and the question I'm going to ask is, how many are white and how many are black in percentage? Okay. So I'm going to run through these electrons totally random. I don't know anything about them. I just know that they're electrons. Right? And there's no preference to be black or white. Right? Electrons are great. And black electrons are the same as white. There's no preference one way or the other. Given that, what do you think the distribution is? 50-50. Exactly. Really, really simple. 50-50. And that's exactly correct, right? It's random, right? It's just a coin flip. 50% electrons will be black and 50% will be white. I'm going to have to move pages. Bear with me. We'll move it over a little bit so you can see it. There we go. Okay, so let's do another experiment. Let's do the same experiment. And we'll put them through the flavor box. And detect them with CCD cameras. All right, what's the percentages, you think? In this case, right? Just random electrons going through the flavor box. What's the percentage? Same. 50-50. It's a coin flip, right? They're just random, right? Nothing fancy. Again, nothing scary here. So now let's try something different. All right, so these are just kind of baseline examples, right? These are just to make sure that our sanity check, that we're not insane, right? And in fact, you go to these experiments, and that's exactly what comes out. 50%, 50%. Now let's do something different. Let's add another box into the mix. Let's do 2 boxes of the same type. So let's do a filtering, right? So let's take an electron and run it through the flavor box. Right? And remember, sweet comes out this way. And sorry, I'm going to erase this. And what we're going to do is we're going to kill. This is like a wall. We're just going to kill the savory ones. We're going to filter out the savory ones. And we're going to feed the sweet ones into a new flavor box. All right. And then we're going to read the outputs. Okay. So at the second box, so let's go again here. So electron comes in, all the sweet ones go into the next box, and all the savory ones just get destroyed. So at the final box, what do we observe at our CCD cameras? How many sweet and how many savory? Want to say it again? 75-25. No. Why do you think that?
Well, the savory ones were destroyed in the first one, so the only expert not savory.
Oh, so let me think about it differently. So you're right about that. So instead, let's think about counts of these. What's the percent of counts? Not in terms of total electrons, but every time the CCD camera clicks. All right, so how many of the detections of the second box, how many are sweet and how many are savory? So we have a 50-50. Any other suggestions? Which one would be 100? Savory. Okay. Well, so you mean savory or sweet? Sweet. So we have a 50-50 and we have 100% sweet. Who believes it's 50-50? From one person. Who believes it's 100? Okay, yeah. Hundreds are right here. Right? Because what have we done here? We've identified which ones are sweet. And then we push them through the box. They're still sweet. Right? They're still sweet. There's nothing's changed. I have a feeling people are saying 50-50 might know more than I think. And you're getting in trouble. I'll come back to that. Let's come back to that 50-50 incorrectness in just a minute. Right? So this works out exactly the way you would expect it. 100% of the clicks at the CCD are sweet and 0% are savory. Let's try something a little different. I'm just going to kind of draw it small here. First, what we're going to do is we're going to run it through the flavor box. We're going to kill the sweets or the savories. And we're going to take the sweets and put it through a color box instead of a flavor box. And then read out how many are white and how many are black. Okay. So what we're doing is we're doing a flavor filtering. And then we're detecting the amount by color. What do you think the answer is here? Yeah, well, 50-50, right? Because flavor's got nothing to do with color. Right? That's what I said, they're orthogonal. They don't have anything to do with each other. Right? So we filtered out the sweet ones, but the sweet ones are still randomly 50-50 black or white. Right? So all the sweet ones go in there and you get 50. All right. Again, nothing crazy yet. Right? And you can go do this experiment a million times. And let me tell you, people have done it a million times. And you get this exact result every time to insane precision. 50-50. Everything's random. Okay, let's throw. Now, let's do something a little weird. Is this 5? Yeah, 5. All right, so we're going to take we're going to take our flavor box, and what we're going to do is add 2 mirrors here. Right, we're going to split. What we're going to do is we're going to split the savory and sweets out and bounce them, and then recombine the beams of electrons back together, and then detect the flavor out. All right, so we're doing 2 flavor experiments. We're separating our sweet and savory apart. And this is a reminder, remember, sweet is collinear and savory is perpendicular here. All right, so let's think about what happens. So what happens in the first box? Well, I split the savory and sweet out. All right, so I've identified, we know what those are, 50-50, right? Right, so they come out of the first box 50-50, and then they're recombined into a different beam, and then filtered through that, and we detect which ones are sweet and savory. What do you think the percentages here are? 50-50. Correct. Now, I'm going to do the same experiment. And I'm just going to erase it. What I'm going to do now is I'm going to now block off the sweet, right, and do this. All right, so this is without, this is combined. And then with sweet block. How many do you think I'm going to see here that are sweet, and how many do you think I'm going to see savory? Right, so what am I doing? So in the second instance, I'm cutting the sweet off, so there's no sweet flowing anymore. Sweets are dead. So what do I see at the end? Just right, it's a savory. Fair enough. Now, what if I were to feed in? I'm not going to write it down. Let's just do this, work it out. Instead of feeding in a random electron, let's feed in a sweet electron. Right, so I feed a sweet electron in here. We've got the blocks in for the sweet line. Will we ever see the sweet electron come up front? And of course, when we see the savory one, if we put savory ones in, we'll see the savory ones come out, right? Because it blocks with the savory. Now, here's where we start to get into weird situation. Let's mix the boxes together. So what we're going to do is we're going to filter by color. And then we're going to filter. I'm going to cut off the blacks. Okay, so we're going to take whites and we're going to put it into our flavor box. And we're going to do the same beam recombination experiment we did before, where we split the beams of the flavors. And then recombine them. Sorry, that's the wrong box. Recombination box I wrote with an X. And then what we're going to do is take that net beam and run it into another color box and ask, what's the color? All right, and then I'm going to ask the question at the detector. There's a detector here on the black as well. What's the white percent and what's the black percent? Okay. So let me just make sure right, these beams are being recombined. Oh, actually, no, they're not. Sorry, I apologize. No, they're not. Okay, so let's look at this experiment, right? We put in random electrons. We filter out the white ones, right? So right here at this box where we split them up, we see 100% white. Do you agree there? Okay, so now what we're going to do is we're going to split them into savory and sweet, and then recombine, and then check the color at the end. What do you think the white and the black percentages are? 100 to 0. I agree with that. All right, so this is with both, we're going to say this with both flavors. All right, we're taking both flavors. Now, I want to do the same experiment, but I'm going to make a modification to it. I'm going to block one of them. All right, so only the savories get through. Just savory. What do we think the percentage are? Yep, still for white and black. Same measurement. All we're doing is we're cutting off the sweets. All right, so okay, so we have 100, 0. So let's go back. Let me just remind ourselves, just and you can come back and tell me if this is right or if you want to change your answer. We're separating by black and white. We only take the whites. And then we're doing a filtering of just the savories. And then we're measuring the color after that. Would you guys agree that it should be 100 to 0? Okay, well, okay. When it comes to numbers of electrons, you're correct. I mean, in terms of the number of, see, every time an electron hits one of the detectors, it will tick it. And my question is how many times? So you're right. And every 100 electrons, when 50 go through. But 100% of them, you're implying 100% of them will be white, right? So your claim, everyone's claim, does anyone want to disagree with that? So everyone thinks the answer is 50 to 100. or 100 to 0, excuse me. All right. You might imagine that now I'm kind of hesitating. This answer is wrong. This is not what you read. Does anyone want to guess what you actually read? 50-50. 50-50. Isn't that interesting? Let me tell you, this happens. This is an experimental truth. People have done this experiment with electrons. They've done it with photons. They've done it with atoms. They've done it with molecules. They've done it with mirrors. People have done this experiment with a giant, I don't know how big they are. They're like 10 meters wide, 10-meter long mirrors at the, what is it called? The LIGO interferometer, the gravitational wave observatory. Do this experiment with those mirrors. Those mirrors are massive. They're on the kilogram scale, and you can reproduce this result. 50-50. When you run through this flavor box, we somehow destroyed all the color information. They've re-randomized. Now notice the interesting thing is that if I let both flavors go through, that doesn't happen, right? I filter out the whites, and then both flavors go through, and we detect the color, and the color hasn't changed. But the moment I cut the branch off, for some bizarre reason, they've lost all their color information. That should ding in your head, what the hell is going on? And it should. It should make no sense. And the only time it will begin to make sense is when we start to understand the theory of why this happens, because this is real. Every particle exhibits this behavior. Every microscopic object. It's material with its properties. Right? There's something about the property of an indistinguishable particle that is ephemeral, in the sense that it's only defined at a certain point, and you can lose that property and re-randomize it. Seems like spontaneous. Right? And so, again, I don't really have an explanation for this. I just have an experimental result. And of course, the question you might have to ask is, well, how does that even happen? Right? How do the black ones end back up over it? Right? And so you're going to start sitting here and thinking, okay, well, how does these trajectories happen, right? Because when I don't have a block here, right, when both savory and sweet are allowed to pass, the color never changes. Okay, so let's think about how the electron is moving through this system. Okay, so again, we're going to take white electrons here and we're going to put them into the flavor box. And imagine that the flavor box is connected so that we can go either path, right? The electron intuitively can go through either path. Right? So maybe 50% go through savory and 50% go through it. Right? That's never changed. But now what I've done is I've put a block here. And they all go through the savory, and that somehow makes them lose their information. But that can't be how this works, right? Because what that implies is that you have a white electron coming into your flavor box. It only has one path, right? So you've got a white electron going through savory and going into there. It should just end up in the white box. Right? Very logical. That's obviously not what happens, because that would predict that you would see all white, but we'd see 50-50. So that means the electron can't be going through the savory like that. Obviously, it can't be going through the sweet side either, because it's blocked off. There's no way to get there. And you know what's even more interesting? You may say, like, so for instance, how does the electron know that this is blocked? Right? You would think that the electron goes through here and then it stops and dies. But let me tell you something very interesting. Imagine if these legs, right, the lengths of these paths, imagine they're a light year. Okay, and right, the size of this experiment spans over multiple stars. Okay, so each step is at a different star, and you're sending an electron between those stars. And the walls are put up
somewhere in the path between those stars, between those devices. All right, so we're talking about huge, huge distances, right? The fastest information can travel is the speed of light, right? So when the electron leaves the flavor planet, and let's say the color box is a light year away, it takes a year for the information to travel to the color box that the electron has come, right? The electron's been sent, right? But the electron, obviously, you can't move at the speed of light. Nothing with a mass can move at the speed of light. So there's going to be a time lag between when the signal, when the flavor box planet signals the color box planet at the end to turn on the instrument and get ready for an electron. It takes a year, and they know that electron's going to take some time to catch up. Right? It might take 2 or 3 or 4 or 5 or 10 years. Right? But if we do things on a nice timeline, we do things synchronized and we all on the same time scale, we all have the same clocks and they're all synchronized, we can have our construction guys go out there at some point in space and put that block in right before the electron comes. Okay. So you put that block in there after the information has been transmitted to the electrons coming, but before the electron hits it. Right? Because so these electrons basically they get stuck and they have no idea that they're stuck. Okay, so when the electrons leave the flavor box, they expect right when they're at the exits, I can go either way I want. Right? The savories go this way, the sweets go that way. Nothing interesting happens. Right? And so at the flavor box, from the flavor box's perspective, it looks as if the entire apparatus is connected so that there is a path here, right, to go to the beam converger, well, the beam combiner, right? So at the flavor box, nothing interesting happens. Half the savory leaves and half the sweet leave, just like what would happen if all the boxes were connected and there was no wall. But then I'm going to put that wall in there. And the moment I put that wall in, all the electrons that I read here become 50-50. So what that means is that the flavor box, right? If I didn't have that wall here, I would read 100, 0 there. But somewhere in the middle of the experiment, I put the block there after the information has been transmitted, but before the electrons got there. And now when I read the electrons, when they get there, I read 50-50. The result of the experiment has magically changed instantaneously from 100, 0 to 50-50 the moment I put the block in. That would imply, right, the only thing that causes the system to go from 100, 0 to 50-50 is the presence of the block. Right? So the moment that block comes in, that would imply that the system magically knows across the entire universe that I'm no longer in this 100, 0 instance, I'm now in the 50-50 instance. Right? If that block's not there, I see 100, 0. If I put the block in there at any time after the experiment started, before the electrons passed it, it becomes 50-50. What that means is that so imagine that means the electrons that are going through the main path towards the color thing, right? We think that at first they were 100 all white, and now they're not anymore, right? And that instant, that change happened when I put the block in somewhere in the middle of the experiment. So what does that mean? Well, that means that the electrons that discover the block say, hey, to the electrons that are millions and millions and millions of miles away, instantaneously, hey, by the way, this is blocked, you're going to be 50-50. So what this implies is that information is traveling faster than the speed of light. Right? By putting this, imagine that the electrons running through here are 10 or 20 light years away from that, right? It takes 20 years for information to propagate across each of the beams. But the moment I put this block here, all the electrons that go through there are now instantaneously 50-50 in color. This happens. Perfect. It's one of the best done experiments ever. It's been done 1 million times. And the same result occurs everywhere. That somehow, when you fuck this experiment up and you go from a situation where you go 100, 0 and go 50-50, it happens instantaneously. Einstein calls this, he hated this idea. And he spent most of his life trying to disprove that this happens. It's called spooky action at a distance. This is actually the term he comes up. Right? He says electrons, this is Einstein. you tell them it's an experiment and you tell them, okay, the only way that this can work macroscopically, right, in your mind, is that the moment you put the block in, all the electrons in this system magically are updated, that there's a block in the way, and they reconvert to this 50-50 mix up. That obviously can't happen. Nothing can travel faster than the speed of light, but the only way to explain this experiment, if it's on multiple orders of magnitude length scales, huge experiment. The only way to prove this, the only way to explain this is that if the electrons that detect this tell the ones that go up on the savory one, hey, I can't get through here, you're going to be 50-50 color. Right? It happens instantaneous. And no matter which length scale you do this, people have done this, bring the block in, bring it out in the middle of the electron, done all these experiments, hundreds and hundreds and hundreds of experiments over many, many decades. And everything leads to this being correct. That the electron somehow, or any particle, somehow magically understands what happens. The information in some ways travels quantum mechanically through these electrons faster than the speed of light. Einstein hated this. Einstein fought tooth and nail for years and years until his deathbed that this cannot be physical. And somehow right, of course, Einstein is really offended because his specialty is relativity, right? Speed of light is his dogma. And what I'm telling you here is that quantum mechanics transmits information faster than speed. So Einstein says, well, this can't be the case. So completely absurd. So one thing that maybe what's happening is that in fact the electron, before it comes into this box, actually knows more information about itself than we do. Right? But the electron has some hidden information that determines the results of the experiment properly. What he calls hidden variables, right? There's some hidden things that don't make this random or any of this. It already has the information it needs to get the right result. We just can't observe it. Hidden variables, hidden kind of parameters that ultimately determine the evolution of the system and to describe this kind of odd result. So he comes up with this, him and two other guys, Podolsky and Rosen, they come up with this paper that kind of characterizes this hypothesis. He comes up with a paradox. He says that assuming that these electrons or whatever, these particles can transmit information faster than the speed of light, this is a violation of something. And so he comes up with this experiment that shows that it's a violation, it's paradoxical. And it turns out that in the 50s and 60s and into the 70s and 80s, experimentally, that not only was he wrong, that it's impossible for there to be hidden information within these electrons. Electrons don't know anything. Right? This entire concept that electrons have some secret hidden information that determines these things that we can't know about, that can't happen. There's a famous theorem called Bell's theorem that proves this. Right? And there's been lots of experiments that show that Bell's theorem is correct, which means that the electrons don't have any information about what's about to happen. No idea. Right? And that the idea of this spooky action concept is actually exactly what describes the experiment perfectly. Right? That's really, really scary. Right? Because I've just explained to you something that makes absolutely no sense. And unfortunately, it's a fact of life that this is exactly how quantum mechanical atoms work, molecules work. And you might say, okay, then that must mean that the theory that explains this must be horribly complex, right? It must be so unlike anything in the universe, right? The physics must be so unphysical, right? It must just seem so alien. In fact, that's not true at all, right? And for the first couple of weeks of this class, we'll talk to you about that logic and those physics. And what we're going to do is we're going to step away from this idea of thinking about particles with trajectories and definite properties, things that are fixed always. Like if I were an electron and I measure me in the color box, I'm always going to come out black. Right? We got to get away from there, and we have to come up with a language. It's really a language. It's not a theory. A language to talk about this kind of thing. And it's a very simple language. The problem with it is it doesn't look like any other language you know. Right? So it's not really complex, it's just very foreign. And once we get through that language and understand it, this stuff will come out and be very obvious. Right? And so there's a couple of take-home points. How much time do I got? 15 minutes, great. A couple of concepts that I want you to take home from this. First of all, is that physics or reality in quantum mechanics is probabilistic, right? Things are random. Right? We're going to see that time and time again. Randomness is one of the central properties of microscopic chemistry or physics, however, quantum mechanics, whatever you want to call it. It's actually, I would say that probability and randomness is the key organizing principle of the universe in general. And the interesting parts about the universe are the things that have magically constructed from this randomness. But we also have this interesting concept of properties, right, that are orthogonal to each other, right, unrelated properties, but somehow they're related, right? Because if I filter through one and then filter through another, I mix up the previous, right? That's what we saw in this last experiment here, right? So that would make you seem like, okay, well, maybe color and flavor are related to each other. Right? Because if I filter color and then filter by flavor, I lose my color information. Right? So maybe color and flavor are related to each other, and there's a very, very, very fundamental relationship between them that is mathematical, and we'll be able to dig that out. Of course, we won't be using flavor and color here. I'll explain what actually these are with the electron when we get to it. I said it's this concept of spin, but I'm not ready to talk about spin yet. And there's a theory that allows us to say, in the spin world, we're going to have color for spin, a flavor for spin, and they're interrelated to each other. And we're going to find that mathematically that if you measure one, you lose information about the other. You have to. Right? That's going to be a law. We're going to be able to determine, the cool thing is that we're going to be able to make a determination. We have a molecule we want to measure properties, or a particle we want to measure properties. So maybe we want to measure its momentum or its color or its flavor. There's going to be properties that we measure. Say, for instance, we can measure color. There's going to be properties that we measure after it that will mix things up, and then there will be properties that we measure that don't mix things up. So for instance, as we'll see, I can measure the color and then measure the energy of the particle, and it doesn't affect the color. Same with energy and flavor. So if I were to change the C or the F, one of them to E for energy, everything that you would imagine was going to, the normal results, right? Everything gets classically moved around, nothing gets mixed up. That's what happens, right? So there are classes of observables, things that we can measure about things that we can measure simultaneously, right? Like color and energy or flavor and energy. But there are things we can't measure simultaneously about something like color and flavor. Right? And there's a rule that allows us to calculate which ones we can measure and which ones we can't together. Right? And it turns out that that is a very, very fundamental property of chemicals, molecules, atoms, microscopic objects. It's just the universe. This idea that there is only so much information that we can actually measure about one thing at a time. Remember, we're limited. And the reason why we're limited is due to this probabilistic idea that things are. Right, so we'll be able to suss out and get in detail the criteria for these things. But what are things that we can measure about stuff? Right, and that's going to be really important because we're going to want to do spectroscopy. Maybe we're going to want to accelerate particles. We're going to want to measure how things flow in a system. For instance, if you think about oxidation or redox reactions, for instance, you're going to want to, if you want to study a redox reaction and know how it works, you're going to want to track that electron as it goes from the reductant to the oxidant. You're going to flow from the anode to the cathode. So it's really important to think about how an electron flows from one molecule to another. So we're going to think about motion. We're going to think about how electrons exist, or how matter exists in chemistry, and how it's organized. So what we're going to see is, the reason why I bring up electrons, it's important, As I'm sure as you know, chemistry is all about electrons. Electrons really all, as we'll see, electrons define chemistry. So I just want to kind of summarize very briefly here. Maybe right on the board. About what quantum mechanics is and what it is and what we're going to be learning this semester. All right, from here on out, I'll just, most of the time when I write QM, I mean quantum mechanics. And I want to talk about what quantum mechanics is to me and what it should be to you and what it isn't and what we're not going to talk about in this class. Because I'm sure Marley can probably vouch for this soon. The way I teach quantum mechanics, the way I think about it is probably very different than the Pavlovsky talk about. And that's okay. Because as we'll find out, quantum mechanics is essentially this very interesting diversity. You can think about it in lots of different ways and lots of different levels. And in fact, there are multiple approaches to quantum mechanics that are equivalent that use completely different math. And we'll talk about that. So I want to talk about what QM is and what it isn't. All right, so what is QM not? And I think it's really important to dispel some kind of ideas about quantum mechanics. Because one of the problems about quantum mechanics is that the people who talk about it in public usually don't understand it particularly well. In fact, I can't remember who says this. Some famous physicist says no one understands quantum mechanics. Anyone who says they understand is a liar. I largely agree with that, but there are shades of understanding. But what we're gonna say is that it's not a universal theory to existence. All right, when you sit and go on YouTube and talk about quantum mechanics with a bunch of people who aren't physicists and stuff, they'll talk about the multiverse and all this junk. Of course, that stuff gets popularized, and they talk about how quantum mechanics, is the key to understanding our universe, and the fact of the matter is that's not true. Just like Newtonian physics, quantum mechanics is partially complete. Right? As we'll see, as you get to really, really small sizes, Newton's laws don't work anymore. I use quantum mechanics, but there's going to be a scale in which quantum mechanics breaks down too. Right? And then there's going to be a new theory that can explain that. And it turns out that theory breaks down too. There's always limits. This isn't me telling you how the universe works. This is me giving you a framework for us to understand and predict how certain classes of microscopic objects work that are relevant specifically to chemistry, right? And it's still effective. It's not a true theory of anything. It's just a way for us to mathematically represent the data, and it works. Right? So there's no, I'm never going to sit here and tell you, we're going to talk about a concept called a wave function soon. And in a wave function, every object has a wave function associated. We can write down the wave function for many different things. And it's just a function. You see, it'll have cosines and sines and e to the x and all sorts of stuff like that. It's just a function, and it represents the system we're looking at. That does not mean a hydrogen atom is a sine function. It just means that we can represent the hydrogen atom and its behavior using sine functions and e to the x and stuff like that. It's a representation of reality, an empirical model that explains the results very, very precisely. Right? So it's not universal. Another thing that always triggers me, let me tell you a story. I was at a wedding in 2018 for a friend of mine who's a lawyer. So most of her friends are scientists, a big corporate lawyer. And my wife was her maid of honor, and we were sitting at a table with all the other people from the bridal party and stuff. And there was a woman there. She was, I don't know what she was, but she had just come back from Tibet, was really into Buddhism and stuff. And she asked me what I did for a living. I said, I do experimental quantum mechanics, because that's what spectroscopy is. And she went on and was like, oh, quantum mechanics, I know that about uncertainty and stuff. I learned about Buddhism and stuff like that, and how it ties into spirituality and stuff like that. And I wanted to blow my brains out. So I just wanted to say that, at least in this class, is that QM is not
a spiritual or religious framework for understanding anything. Right? I don't want you to sit here and be like, oh, now I can understand the brain by using quantum mechanics or the soul. Right? Anyone who says that to you doesn't understand it or is a con man, in my opinion. Right? It's not a religious framework. It doesn't. I don't know how else to say it. We're going to find it, and hopefully you can find the beauty in it in the same way that I do. It's a very beautiful and elegant theory, but it opens a lot more questions than it answers in some ways. And people, because of its intrigue and it's interesting and it's fundamental, people think of it as fundamental, they tend to overcompensate and extrapolate that to the absurdity. And I don't want to deal with that. And so one thing that we can sit here and talk about is, we can talk about this later, about the multiverse and all this types of interpretation and stuff. It's not going to be with this class, right? The philosophy of quantum mechanics is not, the ontology of quantum mechanics is not what's important to us, right? It's a tool for us. It's not a way of being. It's not a spirituality. It's not a dogma, but it's an empirical framework, very, very rigorous empirical framework that allows us to, in our case, interrogate chemistry directly, right? At a molecule level, right? Remember in last semester, for those who were here, we talked about moles, pretty much the entire class, right? Everything joules per mole. We're talking about many, many molecules, 10 to the 20, 10 to the 40 molecules. Right? In this class, we're going to talk about one molecule. Maybe we'll talk about two. Right? We're talking about one molecule by itself. Right? It's a very, very different world. And it's a framework for us to understand and how to grapple with the physics of one molecule or the physics of one atom. Right? What kind of predictions can we make? What kind of things can we measure? All right, so that kind of answers what it is. Right? It is a powerful framework for understanding microscopic behavior. All right, I'm not really concerned about the implications of this. What I'm concerned about is that we are chemists. We don't want to understand chemistry. We want to understand the truth about molecules and atoms. So we need to have a theory that's true, that doesn't bullshit around, and allows us to calculate things precisely. And that's what quantum mechanics is. Very, very powerful framework for this. Nothing more, nothing less. Well, it can be more, but for us, it's not. I'm not going to write this, but I just want to reiterate this in the last 2 minutes. Quantum mechanics, and I'll write this, I would write this for is not and is, because it's true for both. And we're going to see a lot of things in quantum mechanics that's both true and false as well. It's not really fair to say. We're going to see things that are can be two things at once. Quantum mechanics is not absurdly difficult by itself. And find the math's not that complicated. It's really not that much different than regular physics. We're going to have this kind of major shift in understanding how to represent things. And Newtonian physics, when we take physics 1, we think about particles moving in trajectories. They have position and momentum, right? We can measure the momentum and the position as a function of time. Right? That's all good and great. Can't do that in quantum mechanics. But the math at which we have to, instead of looking at positions and momenta and trajectories and stuff, we're going to have to look at different things. And the math that we do that isn't really all that much different than it is for physics. But in order to understand the structure, like this difference between a particle with a trajectory and a motion, like a baseball or a billiard ball, and an electron, we're going to have to represent them differently. Right? And that's where the hard part comes in, is understanding how do we represent a microscopic object with one, and how do we understand that in kind of a practical way, right? How can we hold this in our hand and work with it and mold it to what we want? That's the hard part. It's training yourself to understand these things.
right? Because it's going to require a different way of thinking than other physics courses or other chemistry courses. But every result we're going to come up in this class, you've seen before, right? We're going to understand, right? All of this will get you to the same results that you get in general chemistry or organic chemistry or any other chemistry. But we're doing it for the right reason. We're not going to make any assumptions. We're not going to do Lewis dot structures class, which turn out to be wrong anyway. We're not going to think about structure now. We're not going to think about spectroscopy as an electron getting promoted to an excited state and then coming down to a lower state. And these are approximations. And so we need to come up with a way to rigorously represent these things that is real and is physical and gives you predictions that work at all scales. Right? Really, really good high in spectroscopy and really, really low in spectroscopy. You need a theory that explains everything, and that's what you want to do. Okay, so what I'm going to start with next class is we're going to do a little history. So I'm going to talk to you about maybe 2, maybe 3 different experiments that happened around the turn of the 20th century that showed that really, really obviously, just like my little thought experiment did here, that all is not well with the physics world, that Newton was missing something, right? And Maxwell as well, right? And so we're going to identify those things experimentally because that's the way quantum mechanics was developed. Quantum mechanics was not developed in the vacuum. Quantum mechanics was developed to explain experimental results. So we'll start with the experimental results and work from there. All right, guys, have a nice one. I'll see you next week.